Good morning. Okay, let us start. Uh, in the till the last class, we have learned about the various thin film growth methods. Okay, various thin film growth processes, be it physical vapor deposition or chemical vapor deposition. So today we will learn about this nucleation and growth. Okay, nucleation and growth of thin films. So how thin film growth takes place. Okay. So and also in short, basically we'll learn about nucleation process also. Okay. So this is basically how the growth takes place. So we have learned about various growth mechanisms or growth processes, but the method we don't know yet. Okay. Okay. So there are several steps for growth of thin films. So these steps are absorption, step 1. Step 2 is surface diffusion, then chemical bond formation. Then chemical bond formation yeah, is of two different types. One is like molecule bond formation, and the other one is substrate molecule bond formation. And then microstructure formation, and then bulk changes. Okay. So these are different types of uh, growth mechanisms. Okay, various growth processes are involved for thin films. Okay, so now, okay, so again, absorption, surface diffusion, chemical bond formation, then microstructure formation, and bulk changes. Absorption means absorption of atoms or molecules happen on the substrate. Then these atoms and molecules, they diffuse into the substrate. Okay. Then when these atoms and molecules have already diffused into the substrate, so there would be two types of changes. One will be like bond formation. There would be two types of bond formation, because in order that these atoms or molecules are stable on the substrate, so two different there should be two different changes that we can expect to see. So one is molecular bond formation, because there must be a chemical bond so that the atoms and molecules are stable on the substrate. And the other one is substrate molecule bond formation. So only when these molecules or atoms and atoms are like stable on the substrate, then only thin films can be stable on a substrate. Okay, so this step is also important. And then microstructure formation means the formation of the thin film itself. Okay, the final formation of the thin film, and then the bulk changes refer to like what happens after the thin film is formed. Okay, maybe because of temperature or because of like enough growth time. If the growth time is more than required, then what happens? So that is the bulk changes after the formation of the thin film. Okay, so the first step of growth is absorption. Okay, absorption, and it is also called as physiabsorption. So this note, which you can see here, I have already uploaded uh, this to Google Classroom. So you can find that note in Google Classroom already. Okay, so absorption means an atom may be either reflected or absorbed from a substrate surface. That depends on incoming flux of atoms, trapping probability, and sticking coefficient. Okay, so if I can draw somewhere here, this is the substrate. Okay, suppose this is the substrate. So an atom, so atom from the target. Okay, so when we have learned about various thin film deposition methods, so we learned that so atom from the targets, so they fall on the substrate. Okay, they are incident on the substrate, but that depends on these atoms may get reflected also. Okay, reflected means instead of getting absorbed by the surface, they may get reflected. Reflected means they are not absorbed by the surface, they hit the surface of the substrate, and then they move away. Okay, so yeah, so but now the thing is, how many number of atoms will be incident, or I mean which atoms will be incident on the surface of the substrate, and which ones will be reflected back. That will depend on several possibilities. So one of the several scenarios. So one of the scenarios is incoming flux of atoms. So incoming flux of atoms means how many atoms are getting incident on the substrate per unit area. So that is the flux. So how many atoms? So these are the atoms which are incident on the surface of the substrate. So per unit area, how many atoms are there? Then trapping probability. So what is the trapping probability of these atoms on the substrate? Okay. I mean, what will be the trapping probability? So will they be trapped or they will not be trapped? They will just be sticking to the substrate like that. And sticking coefficient. So sticking means like, so it's a quantity sticking coefficient. So sticking means whether they will stick to the substrate or not. So on various these things, the probability of absorption or physiabsorption will depend. Okay. So yeah, so atom may be reflected or absorbed from a substrate, and it will depend on the various these factors. Okay. Okay, so now, okay, so that is the absorption process, the first step for growth of thin films, and then the next process is surface diffusion. Okay, so absorption, then the surface diffusion. So surface energy. So when we talk about surface diffusion, so this term surface energy has to be considered. So surface energy means like when there are atoms on the surface, etc. So uh, the energy that they experience on the surface, energy means whether the energy like so when see okay, so how can I explain this? So suppose this is the surface of a substrate. Okay, so an atom is incident on the surface. Okay, so it will have some so it must have some energy. Okay, so that energy, because of that energy, this atom gets incident on the surface. So once the atom is on the surface, so it will try to accommodate on the this atom or this molecule will try to accommodate itself on the surface of the substrate. Okay, so accommodate by like a trapping or diffusing or by your this thing stating. So in that case, what happens? So there will be some energy will be created on the surface of the substrate. Okay? Because it wants to undergo, this atom wants to undergo some physical change on the surface of the substrate. So it will experience some energy on the surface of the substrate. Okay, that is the thing. Once the atom sticks to the surface, it creates energy on the surface. So this is due to the surface atoms stretching their bonds in response to the absorption of the film. Okay, so why? Because the surface atoms, they want to accommodate on the surface of the substrate. The atoms, they want to accommodate on the, I hope you understand my handwriting, so I think it should be understandable. So the atoms will try to accommodate on the surface of the substrate, and that's why this surface energy will be generated. Okay. Okay, so the surface energy can be minimized if the atom has enough energy and time to diffuse to a low energy state. Okay, so these atoms which are incident on the surface, so they have enough energy and time. Okay, if they have enough energy and time, then what will happen? So they will, okay, where is it? Minimize if the atom has enough energy and time to diffuse to low energy states. Okay, so let me draw again. Okay, this is the surface of the substrate. Okay, so I hope you understand this. So these atoms from the target or from the source are incident on the substrate. Okay. So now this overall surface energy can be minimized if the atoms have enough energy. These atoms, they have enough energy, and what will happen? They enough energy means they will get diffused into the uh, low energy state. Okay, they will get diffused inside the material. Okay, diffuse means the diffuse means they will move inside. Like what is the what is the process of diffusion? The diffusion means just moving from one medium to another. Okay, so maybe you have learned this process of diffusion in chemistry, I guess. So diffusion means they will move from one medium to another. So from air medium to the medium of the substrate. Okay. So, but how when they can diffuse? So they must possess enough energy, and then they will move through the surface of the substrate. Okay. And otherwise, if they don't have energy, if these atoms don't have enough energy, then what will happen? So in that case, they will just stick to the surface of the substrate. Okay. Instead of this, what you are seeing, if they don't have enough energy, they will stick to the surface of the substrate, and then they will try to accommodate on the substrate, and the surface energy, let me write it as SE, surface energy will be quite high. Okay, very high. Okay, so this high surface energy can be reduced by using atoms that have high energy so that they can diffuse into the substrate. Okay, so now this diffusion rate, the diffusion rate of these atoms on the substrate, it depends upon the temperature. Okay, it depends on the temperature. Okay, so there should be a full stop. The full stop has not been written here. Okay, so anyway, at low temperature, diffusion length increases. Okay, at high temperature, desorption rate increases and overtakes absorption. Therefore, the rate of diffusion decreases when the temperature increases. Okay. Okay, so this when the temperature is low, low means it may not be very low. It depends on the material to material. So at relatively lower temperature, I would rather call it like that. At relatively lower temperature, diffusion length increases. Diffusion length increases means, okay, let me again draw so that at lower temperature, diffusion rate increases means these atoms will diffuse more. The atoms will diffuse more inside the substrate. Okay, the atoms will diffuse more inside the substrate. At lower temperature means suppose let me consider at a temperature of like 300 degrees Celsius. So low temperature means it does not mean it has to be very low temperature like some minus degrees Celsius temperature or like that. No, it may not be. It may be suppose even at 300 degrees Celsius. But what happens at high temperatures? High means at a temperature higher than this, at a relatively higher temperature, maybe suppose 600 degrees Celsius, okay? Or maybe even more, suppose 700, 800 degrees Celsius. Maybe let me consider the temperature to be 700 degrees Celsius. Okay, so at such temperatures, what happens? Desorption rate increases and overtakes absorption. Desorption means that is just the opposite of absorption. So desorption means these atoms, they are not absorbed by the surface of the substrate, but they move away. Okay, they move away and they are not absorbed by the surface of the substrate. So desorption is just the opposite of absorption. Okay. So at low temperature, diffusion length is higher. Diffusion length is higher means more and more atoms can diffuse to the inside of the material. And at high temperature, the desorption rate is higher. Desorption rate is higher means more and more atoms will like dissolve from the material and they will not get absorbed to the substrate. Okay, therefore this last sentence it is written that therefore the rate of diffusion decreases when temperature increases. Okay, the rate of diffusion decreases when temperature increases. Therefore at increased temperature there will be less diffusion. So, what is the relationship between diffusion and what is the relationship now between temperature and diffusion? So, lower is the temperature, there will be more diffusion of atoms onto the surface of the substrate, and higher is the temperature, there would be less diffusion on the onto the surface of the substrate. Okay, so that's the thing. Okay, so these are several steps for the growth. So the main steps are like absorption, then diffusion and chemical bond formation. Okay, substrate molecule structure formation. Okay, so about chemical bond formation, we will study a different topic. Different topic means various. The topic is called various growth modes of the thin films. So that note is also uploaded to, I think is it uploaded to Google Classroom yet? Yeah, different growth modes. That note is also uploaded to Google Classroom. So we'll also learn about that. So in that note, so various growth modes, we will learn about this bond formation. Okay. So what happens? So what type of growth we have if the molecules themselves bond among them? Molecules make form bonds among themselves, or the molecules form bond with the substrate. Okay. Okay. So the next thing is nucleation. Okay. So growth and nucleation. So both steps are very important for obtaining thin films. Okay. So nucleation and growth are two important processes during the formation of thin films. So not only thin films, but for any other materials also, for any other crystallographic or crystal growth also, this nucleation and growth are important factors, okay, important steps. So nucleation, what is nucleation? By definition, nucleation is the first step in the process of a substance changing from one state to another. Okay, when a substance changes from one state to another, the first step is nucleation. Suppose a solid to liquid change, or a change from a liquid to solid, or this when you have to when you have to grow some crystal or something like that. So in that case, from the raw materials, when the main product will be formed. So at that interface, when the substance changes from one step to another, and that interface, we say that nucleation happens. Okay. So that is nucleation. So it is the step when a substance changes from one step to the another step. Okay, another state, one step to the another state. Okay, so nucleation is also, you can also define a nucleation as the process which determines how long we have to wait before a new phase of material appears. Okay, so how long we have to wait, that is determined by nucleation. Nucleation means, in simple words, uh, so in simple words, nucleation means just at the process which separates the material from one step to another step. Suppose just at the beginning of a new phase, okay? Just at the beginning of a new phase, that state is nucleation. Beginning of a new phase of a material, okay? So a material is being generated, or is being formed, or is being synthesized, whatever you call, just at the stage of the beginning. That is the stage of beginning of the materials formation is called nucleation. Okay, so how long we have to wait to get the new phase of the material, so that is also termed as nucleation. Okay, so what are different types of nucleation, and how does nucleation depend on growth parameter of thin films? So that's what we are going to check next. So what is nucleation? Okay, nucleation, what we have learned. So nucleation can occur in any medium, okay, be it solid, gas, or liquid. So nucleation can take place in any of these mediums: liquid, solids, gases. Okay. In a gas, creation of liquid droplets in saturated vapor. Okay, that is nucleation. That is the example. So in liquid droplets, okay, so during winter time, okay, we have seen, we have liquid droplets, and we like they are all over, okay, in your windows, on then grass, so the grass is wet, etc. So what happens? So that happens from the saturated vapor. Okay, when the vapor present in the atmosphere gets saturated, then what happens? They form liquid droplets. So this is a like a vapor to this liquid transformation, to liquid droplet transformation. That is an example of nucleation in a gaseous medium. Okay, so because it happens in gaseous medium. Okay, in liquids, formation of gaseous bubbles. Okay, okay, like ice formation in water. So gaseous bubble, like ice formation in water, that is uh, also an example of nucleation. Then in solids also nucleation can happen. Nucleation of crystalline amorphous and even vacancy cluster are examples of vacancy clusters are examples of nucleation. So are maybe I have noted. So are examples of nucleation. Okay. So in solids also nucleation can happen and nucleation of crystallites. Okay. So suppose you have some materials and from that you have to grow a particular crystal. So just at the beginning of the formation of this crystal, there is a nucleation, okay, and so that we can get the new phase of the material. So basically that is nucleation and your various examples of nucleation. Okay. So nucleation is of two types. So one is this homogeneous nucleation and the other one is the heterogeneous nucleation. So in homogeneous nucleation, nucleation without preferential sites are known as homogeneous nucleation. It requires superheating and supercooling. Okay, just give me a minute. Okay, so nucleation without preferential sites, so for homogeneous nucleation. Preferential site means for such nucleation to take place, there is no material or no base. Okay, so such nucleation can take place on materials without any base. Base means a preferential site, like some support. Okay, nucleation without any preferential site means there is no support for nucleation to happen. So homogeneous nucleation, okay, homogeneous, what homogeneous, what have I written? Homogeneous language or what have I written? Okay, I don't know what is this. It should be homogeneous. What did I write? Let me just think. Language. What is language? No, it's not language. So homogeneous nucleation. I don't know what I have written. Okay, homogeneous nucleation occurs spontaneously and randomly. Okay, spontaneously and randomly. Why? Because it does not grow on any base or what to say, base or support. Homogeneous nucleation does not grow on any base and support, and so it occurs spontaneously. Okay, it requires superheating or supercooling. Okay, so if under conditions of superheating or supercooling, so we can get this homogeneous nucleation. Okay, so now then there is another type of nucleation which is known as heterogeneous nucleation. So this nucleation normally occurs at nucleation sites on surfaces contacting solids or liquids. Suspended particles or minute bubbles also provide nucleation sites. So this is called heterogeneous nucleation. So heterogeneous nucleation, it takes place on nucleation sites. Okay, nucleation site means a I mean, they need base or support. Okay, unlike a homogeneous nucleation, these heterogeneous nucleations must need a base or support for nucleation to happen. Okay, for support, base or support for nucleation to happen. Like the suspended particles in atmosphere. Okay, so you suppose, because you know there are many dust particles in the atmosphere. Okay, and if we have dust particles in the atmosphere, and then they can act as nucleation sites. Site means the place where nucleation can happen. So they can act as nucleation sites, provided like during winter we see fog and we see like this liquid droplets, etc. Because the liquid vapor, they can accumulate around this dust particle, and when they get heavy, they just fall up to the ground. Okay, fall on the ground, then we can get this mist and this thing. So on our window panes or any glass material, we can see this water vapors. So they act as this heterogeneous nucleation sites, and heterogeneous nucleation can happen in suspended particles or bubbles of inside water, etc. Okay, suspended particle means particles like this, which are suspended in air, suppose like dust and etc. So on. So they can act as nucleation sites. Okay, and such nucleation are known as heterogeneous nucleation. Okay. Okay, so we have learned what is nucleation, and also have learned about what are the different types of nucleation. So now nucleation on the growth parameters. Okay, nucleation, how it depends on various growth parameters. So we have already learned in your one of the previous classes that there are two main growth parameters for thin films. Okay, one is the substrate temperature, and the other one is the deposition rate. Okay. So these are two of the main important growth parameters of thin film. So how this nucleation influence the growth parameters? Okay. Okay. So critical nucleus size increases with high temperature. So the barrier for nucleation is greater with increasing temperature. Okay. Okay, so here is something interesting. So substrate temperature. So it basically means to say if your substrate temperature is very high, okay, then it is difficult to do the nucleation. So whatever is written here in the first in these two lines. So if the substrate temperature is very high, it is difficult to get nucleation, because the barrier for, because why? Because the nucleus size, because the nucleation comes from the nucleus. Okay, this nucleus size for growth, it is higher at high temperature. Okay, which temperature means when the temperature is high, then the nucleus size is uh, sorry, the nucleus size is also high, and if the nucleus size is also high, then the barrier for nucleation means in order to in order for nucleation, in order to like facilitate nucleation, uh, so barrier means in order to facilitate nucleation, it will take more time, or you will need more effort. So therefore the barrier is greater means you have to work more, or you have to deposit for a longer time, or you have to like process for a longer time in order to get your desired thin film if your substrate temperature is quite high. Okay, so you have to remember this: higher substrate temperature means it will be difficult to get the desired nucleation, and if desired nucleation is difficult to get, so the thin film obtaining thin film will take even longer. Okay, so barrier of nucleation is greater with increasing temperature. So higher is the temperature, it will be more difficult to do nucleation, and subsequently uh, the growth of the thin film. Okay, so now deposition rate. So critical nucleus size decreases. Okay, so earlier I wrote increases, but now a critical nucleus size decreases with increasing deposition rate. The barrier for nucleation is smaller with increasing deposition rate. Okay, so deposition rate is just opposite to this substrate temperature. So higher is the deposition rate. Okay, higher is the deposition rate means the nuclei formation or the nucleation process will be easier. Okay, higher deposition rate means nucleus for nucleation process will be easier because the critical nucleus size decreases. Okay, critical nucleus size means the size of the nucleus which is required at the time of nucleation. Okay, nucleation means just when it begins to grow. When the new phase of the material begins to grow, that is the critical nucleus size. So at that stage, we get the critical nucleus size. So this critical nucleus size is smaller when your deposition rate is higher. Okay. So deposition rate you can you can change this during your deposition of thin films. Deposition rate means at what rate you are ejecting atoms from the surface of the substrate or the target. Okay, so higher is the deposition rate, this nuclear size will be smaller. Okay, and now the barrier for nucleation is smaller with increasing deposition rate. Okay, the barrier for nucleation is smaller. So barrier for nucleation is smaller means so nucleation can take place easily or nucleation can take place without with less effort. Nucleation can take place with less effort. So unlike the previous case with of substrate temperature, in case of substrate temperature, nucleation needs a lot of effort. Okay, because higher temperature means higher nuclear size, and nucleation would take greater effort. But in this case, when the deposition rate is higher, that higher deposition rate will facilitate easier nucleation. Okay, because higher deposition rate decreases the critical nucleus size. Okay, the barrier of nucleation is smaller with increasing deposition rate. Okay, so higher is the deposition rate, higher sooner or better will be your nucleation of thin film. Okay, so that's it. These are the two factors on which nucleation depends on various growth parameters of thin films, so substrate temperature and deposition rate. Okay. Okay. So I think that's all for today. Or can I show you something quickly? So this note is already there in a Google Classroom. And I can show you this growth modes, okay, various growth modes of thin films. In a figure, just let me see if I have the figure or not. Okay, I have got the figure. Let me quickly show it to you and discuss. And then, okay, I hope all of you are able to see this figure. So here, three types of growth of thin films have happened. So one is called the this thing, Frank van der Marwijk growth. The other one is Stansky-Krastanov growth. And this third one is Vollmer-Weber growth. So what happens in the Frank van der Marwijk growth? So we get uniform thin film. Okay. So here, this molecule bond formation is stronger. Here, so we talked about bond formation during growth. So molecule oh, sorry, okay, molecule bond formation is stronger in case of Frank van der Marwijk. So these are people's name, okay? Frank van der Marwijk, Stansky, Krastanov, Vollmer, Weber. These are names of some people or scientists who worked on this field. So three types of growth. In one type of growth, molecule interaction is stronger. Now in Vollmer-Weber growth, here you see we get islands. Okay, so these are islands. This is one island, and this is another island. So in this case, molecule substrate bonding is stronger. molecule substrate. Molecule substrate bonding is stronger, and therefore we can get to see islands like this. Okay, so molecule, so instead of making continuous thin films like this, so we get islands like this. Okay, because molecule substrate bonding is stronger than molecule molecule bonding when it is about Fulmer-Weber growth. And the other one is Stransky-Krastanov type growth. In Stransky-Krastanov type growth, so we get to see both the Frank van der Merwe type growth and Fulmer-Weber type growth. Okay, so both we can get to see in Stransky-Krastanov growth. So you see, first there is a layer formation like this, because in that case the molecule-molecule interaction is better, stronger, and then we can get to see the this formation, this island formation. Okay, so here we can see both molecule-molecule bond and island and substrate molecule bonding. So these are three different types of processes by which thin films can grow. Okay. So Frank van der Merwe, Fulmer-Weber, and Stransky-Krastanov. So about this we'll discuss in next class, and also the note I think already given to you. So if not, I will check, and then next class let me check. Different growth modes. Yeah, the note has been already given to you. So then the figure has not been given. So I will also attach this figure to that note. Okay.